Let's talk about complex numbers. First, let's figure out what is an imaginary number I. I is called an imaginary number because we were looking for a number that if you multiply it by itself, so if you multiply I by itself, you want to get -1. Therefore, we define I to be square root of -1. And we can assume that I squared equals -1. In real values, that's not possible that you multiply a number by itself and you get negative value. Therefore, we assume there is an imaginary number, and we use I for that to represent that number. Okay, so I is defined to be square root of -1. Every negative number underneath the square root could be written in terms of I. So if you have a square root of a negative number, you can write it as two parts. Here as a square root of -b, assuming b is a positive, so the total underneath the square root is negative. You can write it as I square root of b because you can split it as square root of -1 times b, which is square root of -1 times square root of b. And this is what we call it as I. So we have I square root of b. For example, if you have square root of -5, you can write that as square root of -1 times square root of 5. This is how you can think about it. And square root of -1, we define it as I square root of 5. Okay, so every time you have a negative number underneath the square root, you can write it as an imaginary number multiplied by a specific constant. Square root of -9, you can write it as I square root of 9, which is simply I times 3. Normally you write it as 3i. You do not write I times 3. But square root of 16, square root of 16 is a positive value underneath the square root, so it doesn't really need anything. It is simply 4. There is no I involved. If it was square root of -16, then in that case, you would write it as I square root of 16, which is 4i. Okay, so there is no need if you have a positive number underneath the square root. How about if you have radicals divide by each other or multiply by each other? If there are negative number underneath the square root. So first you always write it as imaginary number multiplied by a constant, then do the multiplication. So here in these two examples, if you have square root of -25 times square root of -4, you cannot do this. Do not do this. This is not correct. So this is a mistake if you do this. Because the outcome becomes the square root of a positive number, which is 100, becomes 10. This is if you multiply. This is not an equal statement. Because if we write this as a complex number, so this is not correct. I'm going to show you the correct version. The correct version is you can write it first as complex number I, imaginary number I times square root of 25 times square root of -4 is I square root of 4. Square root of 25, simply 5. So I have 5i times square root of 4 is 2, so another 2i. What do I get is 5 times 2, 10 I squared. And what is I squared is -1, as we defined it earlier. So this is 10 times -1, -10. If you multiply the inside the square roots together, you will end up with a positive value. It is not correct. Do not do that. So normally you write this imaginary number times a constant, then you deal with it. So next example would be I square root of 8 times I square root of 2. Now that underneath the square roots are positive, you can multiply them together. I times I becomes I squared. Square root of 8 times square root of 2, 16. You can write it, the I squared is -1, so I have -1 times 4, -4. You can skip some steps after a while. The same goes with the fractions. Square root of 50 is I times square root of 50. Divide by I times square root of 2. You can cancel out the i's, divide by each other. Square root of 50 divided by 2, square root of 25, simply 5. Okay, so make sure that you write this imaginary number if there is a negative number underneath the square root. we have you can write any number, any complex number, as a combination of a real part and imaginary part. So here, the standard form of a complex number is a plus bi. A is what we call a real part, and bi is the imaginary part, the part that contains imaginary part, the part that contains I. A and b, those are both real numbers. It could be 2, 3, square root of 5, doesn't really matter, as long as they are real values. I is the one that makes the bi to be imaginary. So here, in the next example, look at these two. If they ask you to write in standard form. What you do is they want you to write this a plus bi. So here, let's get rid of that negative underneath the square root. You will have square root of 16, I square root of 16, 3 minus I times 4. That is, you can write this 3 minus 4i. And if you compare, a is 3, b is negative 4, and we still have the I. How about the next one? Here, you can write this fraction in terms of two separate fractions. 2 divided by 3 minus 5i divided by 3. They have the same denominator, so it's the same as 2 minus 5i divided by 3. So you can split the fraction in two parts. 2/3 is a. I'm going to write it this way so you can see and compare. I can write the I up front. It doesn't really matter. I can put the denominator 1 underneath it and say this is 5 over 3 times I over 1. But it's unnecessary to write that divide by 1. So here, this is A, and that is B. So what we wrote is A plus BI. So you can split this into two fractions. The same here is a combination of the last two examples. First, write this 2 minus I times square root of 9 divided by 2. You can rewrite that as 2 minus 3i square root of 9 is 3 divided by 2. You can split it into two fractions, 2 over 2 minus 3 over 2i. You can simplify it a bit more, 1 minus 3 half I. It's in the form of a plus bi. So the standard form of a complex number is just you write this imaginary part, real part plus the imaginary part. By the way, you can have 0 as the real part, so you can have something like 0 plus 2i. That is still a complex number. This is simply 2i. Okay, the other way around is possible too, but 1 plus 0i is simply 1. This is just depending on the real value, doesn't really depend on the imaginary part, but still considered as a complex number. Okay, let's talk about operations. Let's start with the powers of I. Powers of I is just for when you, later on, when you multiply complex number to each other, and as the power becomes larger and larger, you want to simplify it. So you want to reduce down the power as if possible. So here, I to the power 1 is basically square root of negative 1 or just I. I'm going to use I. How about I squared? We know this one already is negative 1. How about I cube? I cube, you can think about it as I squared times I, because you should add the exponent. I squared times I to the power 1 is I to the power 2 plus 1, 3. So I squared is negative 1. I to the power 1, simply I. So this product is negative I. So I cube becomes negative I. How about I to the 4? I to the 4, I can think about it as I squared times I squared. I squared is negative 1. Again, I squared is negative 1. If you do this multiplication, negative 1 times negative 1 is positive 1. This is negative 1 times negative 1. Multiplication here. How about I to the 5? I can do this. I can write it as I to the 4 times I. Why am I using I to the 4? Is just because I to the 4 is very simple. It's simply 1. I can say this is 1 times I becomes I. How about I to the 6? I can use again I to the 4 times I squared. I to the 4 again is 1. This is 1. So 1 times I squared. I squared is -1, so 1 times -1 is -1. There is a pattern. I'm going to write it here. Maybe use a different color. Here. I to the power 1 became I. I to the power 2 became -1. I to the power 3 is -I. I to the power 4 became +1. I to the power 5. We went back to the first one. I to the power 6. We calculated just now. Went back to -1. I think you can guess the next one. I to the 7 is going to become -I, and so on. I to the 8, again 1. So every 4 power, every 4 loop that you do, you'll go back to the original position. That's just because I to the power 4 is simply 1. So when you multiply the next I, you go back to starting position of I to the power 1. This helps with calculate higher power. So if you want to calculate something like I to the power 23, you don't want to do all these breaking down. So I know that if I write this as I to the power 20 times I to the power 3, I to the power 20 is 4 times 5. So that means I to the power 4. This means I to the power 4 5 times. But I to the power 4 is simply 1. So this part is simply 1 to the power 5, and you still have the I to the power 3. 1 to the power 5 doesn't really matter. So what do I have is I to the power 3. It's just the leftover from the 20. The I to the power 20 is simply 1. You can ignore that part. So what is I to the power 3? We knew I to the power 3 is simply -I. So basically what you need is these 4. You know these 4? Then any other power only depends on these 4. And you don't need to memorize. You can always calculate. Even negative numbers. I to the power -15. I'm going to think about it as I to the power -16 times I to the power 1. -16 plus 1 is going to give me -15. I want the leftover to have positive exponent. That's why I use -16. I to the power -16, again, it's I to the power 4 to the power -4. I to the power 4 is 1. This is 1. 1 to the power -4 is still 1 times I to the power 1. I to the power 1 left is just I. So any other power, if you want to calculate I to the power 205, for example, just find out that if you divide 205 by 4, it's 5 times 4, 20, 1 times 4, 4. There is the remainder. So that means I can write I to the power of 205 as I to the power, I to the power, 204 times I to the power this remainder, whatever that remainder is, 1. This part is a multiple of I to the power 4. I to the power 4 times 51. This is simply 1. Because every I to the power 4 becomes 1. So what is left is just I to the power 1. As an example for yourself, try I to the power 2019. I'm going to be 1 year behind. 2020 is too easy. Let's try this one. Let's see what you get. Okay, these powers are just going to help if you later on you raise a complex number to very high power. You can simplify it and reduce the exponents. How about adding and subtracting complex number? That is no different from adding and subtracting complex numbers or dealing with variables. You look at the similar like terms. So you combine like terms. If you have -2, for example, plus 5i, if you want to add it to 3 minus 2i, what you do is you add the like terms, you add the real parts together, these two together, you add the imaginary parts together. So -2 plus 3 is 1, 5i minus 2i, 3i. And it's already in the standard form. How about if there is subtraction? You can subtract them from each other. Normally, I will suggest that you get rid of the negative sign by distributing. This way you make less mistake. So I'm going to write this -2 plus 5i and distribute that negative in between. -3 minus minus becomes plus 2i. So now just add the like terms. -2 minus 3 is the real part. It becomes -5. 5i and 2i, 7i. Okay. And if you do it in one step, it is possible. -2 minus 3 becomes -5. 5i minus -2i becomes 7i. It's nothing super complicated. It's just add like terms together. How about multiplication? Multiplication follows the same idea that you do again for linear equations, polynomials. When you multiply them together, you still follow the same rule here. You normally use the distributing property. What is the distributing property? You probably will call it foiling, multiplication, distributing, either way. Here, you multiply each term to the other ones. I have my -2 plus 5i times 3 minus 2i. What do I do is -2 times 3 minus 6, -2 times -2i, positive 4i, 5i times 3, this is 15i, and 5i times -2i becomes -10. I times I is I squared. Be careful here that when you multiply these two, you multiply i's together as well. I times I becomes I squared. Do not write I. Okay, so I have -6. I'm going to try to simplify. 4i and 15i is 19i. And I have -10i squared. But we learned that I squared is simply -1. So 10 times -1. Instead of I squared, you can use -1. And there is multiplication here, not subtract. So -10 times -1, this part is simply positive 10. Positive 10 and -6 is 4, and you still have plus 19i. So this is the result of this multiplication, and it is in the standard form. It's not necessary to write in standard form, but it's good that it's clear if you later on you want to multiply it to something else. If there were 3 of them, for example, if this was -2 plus 5i times 3 minus 2i times 5 minus I, what you do is first multiply these two, as we did, and the outcome becomes 4 plus 19i. Then multiply that by 5 minus I. Again, you need to distribute and calculate. So this way, writing it in the standard form and simplifying helps if you have more than one multiplication. Okay, how about if there is power, something like -2 plus 5i squared? Well, there is no different. You can always write it as multiplication. -2 plus 5i. Squared means multiply by itself. Distribute. If you distribute, what you get is -2 times -2 plus 4. -2 times 5i minus 10i. 5i times -2, -10i. And 5i times 5i, positive 25i squared. Again, I squared is simply -1. You can replace -1 for that. So what you get is 4 minus 20i, minus 20i plus 25 times -1. And I could have written -25. But I just wanted to write it so you know what is going on. Minus 25. Instead of the I squared, we replace negative. And add -25 and 4. This is -21 minus 20i. And this is the result. Do not add -21 and -20. Those are real and imaginary parts. You cannot add them together. So we talked about addition, multiplication, subtraction. Before we talk about division of complex numbers, let me introduce this complex conjugate, because it is very useful for division. So if we have a complex number a plus bi, there is another complex number exactly depending on a plus bi, a minus bi. which is they have the same real part. The imaginary parts are opposite of each other in terms of sign. If b positive, then negative b becomes negative. If b is negative, then negative b becomes positive. So the two numbers are conjugate of each other if the real parts are equal and the imaginary parts are opposite in terms of sign. What's the use of it? So let's see their multiplication. Let's multiply a plus bi times by a minus bi. There's a property that if you multiply two conjugates together, two complex conjugates together, outcome is always a real number. And there is no imaginary part to it. So let's try it. A plus bi times a minus bi. A times a becomes a squared. A times negative bi becomes minus abi. Bi times a is plus bia or abi again. And bi times negative bi is minus b squared I squared. B times b squared, I times I squared. You see that minus ib plus abi and negative abi will cancel out. I have a squared minus b squared, and instead of I squared, I can replace negative 1. Negative 1 times negative becomes positive. So the outcome is simply a squared plus b squared. If you multiply two conjugate numbers to each other, the outcome is always a real value. There is no I involved. There is no imaginary part. And it's simply the real part squared and the imaginary part a squared plus b squared. You can skip steps if you multiply in two complex conjugate. I suggest that you do it for at least a couple of examples, then you will see the pattern. So for example here, you're given these complex numbers and they ask you what is the complex conjugate of 2 plus I. That is, the real parts should be the same, the imaginary part is the opposite. They do not ask you to multiply, it's just that the complex conjugate of 2 plus I is 2 minus I. The complex conjugate of negative 1 minus I is negative 1, the real part is the same, the imaginary is the opposite, plus I. How about the complex conjugate of 3i? The real part here is 0, by the way, 0 plus 3i. So the complex conjugate would be 0 minus 3i. It's not necessary for you to write the 3i and the 0 part. You can simply say negative 3i. So the complex conjugate of 3i is negative 3i. The complex conjugate of I plus 2 is not I minus 2. Do not write that. This is not correct. Because the order here you should look at is what is the real part. The real part is 2. So it is 2. Instead of the positive I, you should have negative I. This I plus 2 is 2 plus I. You can think about it that way. So if the rearrangement is complex part, imaginary part, then complex part, you should still be careful that you pick the complex conjugate properly. Okay, so let's use these complex conjugates here for the division. It helps with the dividing. If you have two complex numbers divide by each other. First, let me mention that you can never cancel out these two. You have additions and subtractions. I already mentioned in the last lectures. So make sure that you cannot cancel out those two. Okay, so what do we do? Normally, if the denominator, if you had something like 2 plus 3i, divide by 2, as we did earlier, you can write them separately. Say this is the case. I'm going to write this two separate fractions. So we're going to use this idea here. But the denominator is a complex number. So our idea would be to somehow try to get rid of that complex part in the denominator. What do? We try to make the denominator to be a real value. So we multiply the denominator by the complex conjugate. 3 plus I is the complex conjugate. But whatever you multiply in the denominator, you should multiply exactly the same thing in the numerator. And by doing that, let's multiply and distribute to see what we get. 2 times 3, 2 times I would be 2 times 3, 6. 2 times I, 2i. 3 times I plus 3i. and I times I squared. Denominator as well, 3 times 3, 9. 3 times I, positive 3i. Negative I times 3, negative 3i. And negative I times I, minus I squared. Again, you expect the denominator to turn out to be a real value. Otherwise, you've made a mistake somewhere. Numerator, instead of I squared, you can use -1. These two are both -1. The denominator is 9 minus -1, which is simply 10. And you see that you have a real value. And how about the numerator? You have 6 minus 1, 7. Sorry, 5. 6 minus 1 is not 7, it's 5. And 2i plus 3i, this is 5i. And now I can separate them and say 5 over 10 plus 5 over 10i. And you can simplify it if you want. 1/2 plus 1/2i. And this is the result of this division. And it's in the standard form of a complex number. How about the next example? You might ask, this is a power, it's not division. So think about negative exponent, -1. If you have something like 3 to the power -1, this means 1 divided by 3 to the power 1. If it was 3 to the power -2, it means 1 divided by 3 to the power 2. So if you have this term, 2 plus square root of 3 to the power, 2 plus square root of 3i to the power -1, it means 1 divided by 2 plus square root of 3i. That's what is given. And they ask you to simplify and calculate this division. So what you need to do is multiply the conjugate. 2 minus square root of 3i. 2 minus square root of 3i. To both numerator and denominator. Numerator is simply 2 minus the square root of 3i. If you multiply the 1 to each one, doesn't really make any difference. Denominator, distribute this times that, times this one, so on. 2 times 2, 4. 2 times negative root 3, negative 2 root 3i. Square root of 3i times 2, positive 2 square root of 3i. I'm just going to put them in order. Constant first and the square root and the I. And square root of 3 times square root of 3i times negative square root of 3i, it becomes negative square root of 9, which is simply 3i squared. Okay, square root of 3 times square root of 3 is simply 3, the square root of 9. And denominator, you can cancel out these two. I squared, what is I squared, is -1. So I have -3 times -1 is positive 3 plus 4. Denominator is 7. And you have 2 minus square root of 3i. Again, you can write them separately. 2 over 7 minus square root of 3 over 7. And this is the result of this division. Here, one more example. One last one. What is the complex conjugate here? Let me erase this part. Oh. What is the complex conjugate? Complex conjugate here. Let me erase. This is 0 plus 3i, as we did earlier. So the complex conjugate of 0 plus 3i would be 0 minus 3i. So simply you can say it is -3i. Again, you cannot cancel out the i's with each other. You can split it into two fractions, but it's going to be useless. I'm going to multiply complex conjugate -3i. Complex conjugate of 3i is, you can think about 3i as 0 plus 3i. So therefore, the complex conjugate would be 0 minus 3i, which is just simply -3i. If I do the multiplication, 2 times -3i is -6i. I'm going to distribute the numerator. Plus I times -3i is minus 3i squared. And the denominator is 3 times 3 is 9. You have -9i squared. Finally, you can, every time you see I squared, you can write -1. These two are both -1. -1 times -3. I'm going to put them in order. There's 3, and you still have -6i. Denominator, -9 times -1. Do not subtract them from each other. This is multiplication. This is +9. And split it into 2 fractions. 3 divided by 9. Sorry, minus 6 divided by 9i. 1/3 minus 2/3 i. And it is in the standard form of a complex number. And this is how the division goes. Every other division is very similar. Just make sure that you pick the correct complex conjugate for the denominator. Okay, I'm going to stop here and continue next time.